get an application now purely to group theory, and this is also useful in many other contexts. So let's look at covers of graphs. So here's the following theorem. Even though I call it a theorem, it's actually easy. Theorem, and theorem is that a cover, let's call it P from x hat to x equals mod gamma of a graph is let's say just the graph morphism is more precisely induced by a graph covering, which is, we know graph morphism, which satisfies the appropriate covering property. Well, let's call it something else. So P, so phi or something from gamma hat to gamma, and mod x hat is mod x, mod of gamma hat. So our so P is going to be the induced morphism graph covering. So every covering is a graph covering. That is the theorem that we are proving here. Okay, and that's a really easy. So we given just one idea proof. So which is, how would we define gamma hat? Define V hat is simply P inverse of V. So this is discrete. It's a set, but E hat is going to be lifts of E in E. So given any edge, you can also think of it as a path. So we have an edge E. We can also think of this is mod gamma, and this is x hat. We don't know what that is, but given any edge, we can look at all its lifts as a unique one given any initial point and declare them to be the set of edges. Okay, and so then it's quite clear what the initial point map is, lifts of E. Okay, so this is, if you wish, E hat, E lift of E in E, and initial point of E hat is just E hat of 0, if you wish, which belongs to V hat. And now it's routine to verify that this is a graph, and the geometric realization is going to be the cover because it's a local homeomorphism, and that we have the graph morphism, which will take E hat to E, and this is a covering. Okay, and why I'm repeatedly saying easy, it does take work, but it's a very good exercise. So I'm not going to do it now. There's nothing gained by that, but a lot gained by doing it yourself as an extended exercise. We'll post it in the course also as an exercise. Okay, so this is nice. So corollary here is the theorem of Fringe. Corollary is that the fundamental group of x hat is free. That is, of course, I assume it's a connected cover, and hence we get the theorem. This is called the Fenchel-Nielsen theorem. Okay, so any subgroup of a free group is free. So this is a non-trivial group theoretic result. In fact, quite non-trivial. It was proved by Fenchel-Nielsen. Nielsen has a sharper version of this. Okay, and you use Schreier normal form and so on. There are various results in combinatorial group theory which sharpen this. But this is a very fairly simple topological proof. But we didn't quite prove it. So proof is just that if F is the free group on S, okay, then F is pi 1 of wedge of S1 with S in S. Okay, that is to say, for each we pick a base point x0, and for each S1 we take an edge here. Okay, so it would be better, instead of writing this as a topological space, so we take gamma with V equals just x0, and E is S union S bar. Okay, and there is only one such graph, So this is equal to gamma gives you this. So the geometric realization of this graph is going to be the free group generated by S. We already saw that maximal tree is x0. Okay, so this is this, and then there exists a cover. This is locally simply connected. So given G and F, there exists a cover with pi1 of x hat is going to be equal to G. And now we know pi1 of x hat. X hat itself is the realization of a graph. So it's the fundamental group of a graph is free. So any subgroup of a free group is free. Okay. This is not obvious, but anyway, we'll make a couple of further remarks. This is a much advertised application of topology, maybe a little bit over advertised. So I'll make a couple of remarks to slightly justify how this sort of thing is quite important. So firstly, we have an addendum. What is the addendum? Okay, so suppose everything is finitely generated. Okay, so if S is if cardinality of S is n, so F is, so in that case we will denote the free group as the free group on n generators. Okay, and G contained in F has index k, so it's a finite index subgroup. Okay, then G equals Fm, where what is M? M is, well, we know we have a graph here with vertices equals 1 and what I called E hat, mod E hat, the number of pairs of edges, is going to be n here. So if I take an m-fold cover, this has n times m edges. Sorry, k-fold cover, n times k edges, and it has k vertices. Okay, because I took a k-fold plus 1, which is n into k minus 1 plus 1. Now you see, if k is greater than 1, that is other than with subgroups of z. Subgroups of z are all z as long as they are finite index. But if it's k is greater than 1, this grows. And indeed in the pictures we saw of covers, for example, I took the wedge on 2 circles and I had a cover by taking maybe a 3-fold cover and then taking loops. Okay, so let's just count. In fact, even better than counting, let's make things effective by looking at a maximal tree. Okay, so here we go from here to here. This is already a maximal tree, and the number that are excluded by this is this one, this one, this one, as well as this edge. So the free group, so there's a 3-fold cover and a free group of 2 generators, and it was a free group on 4 generators. This is a rather important warning because we tend to think of subgroups of a free group as, or any group being smaller. However, finite index subgroups of a free group are bigger than the given group. Okay. Also, this is another cautionary example because you would have seen the Schroeder-Bernstein theorem in set theory, which says if one group, one set injects into the other and vice versa, they're isomorphic. But that's not the case here. A free group which is with fewer generators injects just by looking at the first few generators, and but free group on more generators also injects often. Okay, so you can have, so remark, what I'm saying is that we have F2 contained embeds in F3 and F3 embeds in F2. Okay, that's my first point. We can refine this and we learn some things a little surprising, but 2 more points I want to say. Okay, one is that a converse holds, not literally, okay, in the sense that you can of course have groups. So what would a converse be? So this is saying that if you have a subgroup of a free group, okay, then that is free. What if a group has a subgroup that is free? Well, that doesn't mean anything at all. But what if it has a finite index subgroup that is free? Okay, well, that's still not enough because you could have product of a free group with a finite group. Okay, but the best you can hope for is the following, which was a conjecture of Serre. Okay, so the conjecture of Serre was the a theorem of Stallings, and that showed the following. So the deep theorem is that if you have a group which is torsion free and contains a free subgroup of finite index, then the group itself is free. This was conjectured by Sayre and proved by Stallings using topological methods. Okay, much more elementary result, but which is useful, is also if I take a free group Fn, n is finite, and I fix k index and ask how many subgroups there are of index k. This number is finite. You can prove that using covering spaces, and from that you can deduce the same result for any quotient of a free group, what are called finitely presented groups, which we will see.